Thank you for the introduction and for the invitation to speak. And this is meant only in part facetiously, but for the opportunity to write these notes, which trying to write these notes, which I think we learned a lot as well. So hopefully somebody will look at these notes. At this point, I think even the co-authors hope each other will look at the notes. So I want to talk, maybe to begin with, I just want to draw some pictures, which I'm not sure I want to amplify on too much in this lecture, but maybe just to have something visual to complement all the things that Toby wrote. So that's a line. So that's a simple example of a scheme. And that's a line in A3. So that's an simple example of a closed subscheme in a larger scheme. And now, when I draw this fuzzy thing around the line, what I've drawn is I've taken the formal completion of that line in A3, and that's an example of a formal scheme. And that will be a formal scheme whose underlying reduced scheme is the line, which is one-dimensional, and whose, as a kind of formal scheme, is three-dimensional, because the formal directions fill out the A3. So it has, if you like, one algebraic direction and two kind of formal directions that are kind of transverse to the algebraic direction. And so, so if you were to look at the dimensions Toby wrote down, there was D choose 2. Well, every dimension Toby wrote down had a +1 because everything was over ZP. And so ZP contributes one dimension because it has codimension 1. So if you were to kind of work over FP instead, then that +1 will go away. So then you might have this number, and then you would have this number, D squared, and that will be for GL2, for GLD. But if you were to do, say, PGLD, because you wanted to fix determinants, because they're annoying, and so you wanted to get them out of the picture, then this could lose one dimension. And then when D equals 2, if I didn't screw it up, this is 1 and this is 3. And so now this is a picture, this could be a toy model for what this stack looks like. And so that could be a toy model for the stack for GL2, or PGL2 over QP. And it's, the only thing is that has one irreducible component, whereas in the underlying reduced, there's one irreducible component, whereas our stack, as Toby said, is the underlying reduced is equidimensional, but it's not a single irreducible component. There's some saying it's equidimensional has some content because there's more than one irreducible component. And so to make this picture look a little more like our stack, you could draw two lines crossing in A3 and take the formal completion of that. And so that's actually a very, very good model for what our stack looks like for D equals 2. It shows, the thing it doesn't show is it doesn't show anything stacky. So this is a formal scheme whose underlying reduced has dimension 1, equidimensional with two reducible components, and which kind of its formal directions have dimension 3. So that's the kind of scheme version of what our stack could look like. What's going to happen with the stack is that when you draw this geometric picture, these lines have to become higher dimensional. Because if someone hands you a one-dimensional stack, what they might hand you, you look at it, you think they're handing you a plane. But secretly underneath, there's some wheel turning, which is maybe some GM that's quotienting this plane out. And so if you have your plane modulo with GM, the dimension of the stack is 2 minus 1, which is 1. And so that's what's going to happen in our stack. But still, this is a kind of a good picture. And there'll be some points in our stack which are very close to being schemy. So at every point in our stack, even if you fix determinants, there will be automorphisms, because as Toby explained, by Fontaine's theory, each point corresponds to a Galois representation. And the automorphisms will just be the automorphisms of that Galois representation. And so as a lot of people here, well, actually there's a lot of people here, so I don't know what a lot of people here know, but some people here know Galois deformation theory. And at least for Toby and myself, that was kind of the training in our background that led us to thinking about this kind of a thing, and that's how we approached it from the point of view of deformations of Galois representations. And so if you're from that school, you know that the kind of irreducible Galois representations have trivial automorphisms, but trivial automorphisms doesn't actually mean the trivial group, it means scalar automorphisms. So that is a GM. And even if you fix determinants, fixing determinants is basically replacing GLD by SLD. SLD still has a non-trivial but finite center. So if you kind of were doing like two-dimensional things with fixed determinant, at an irreducible Galois representation, the automorphisms will be a mu2, the center of SL2. So every point has at least a mu2 of automorphisms, but as far as stacks go, that's not such a bad group of automorphisms. Like it's pretty non-stacky. And so this will be a very good model for what happens, for example, at a two-dimensional irreducible row bar. And in fact, again, some people here will know about the weight part of Seth's conjecture, and more of you will know something about it when I finish the lecture, because I'll talk more about it. But they will know that an irreducible row bar has two Serre weights. In the old days, that was kind of theta cycling, a la Tate, Jochnovitz, Serre, and Swinnerton and Dyer. And that's what these two components will be. And so the way the way you make this stack at all psychologically, so this stack existed for a long time in chalk diagrams on Toby's blackboard in the basement at Northwestern before it became kind of written mathematics. And because it existed as these pictures, it was called the picture. And so Toby and I started talking about the picture back in 2011, around the time Fontaine visited us at Northwestern. And it existed just as the picture for a long time before it was finally worked out as kind of written mathematics. But where the picture came from was exactly the kind of example that Toby talked about, where you write down maybe a power of the mod p cyclotomic character, and then a trivial character, and then you say, how could I kind of, starting with this as a kind of a skeleton, how could I flesh it out to a Galois representation? And well, this I is kind of a discrete thing. Like if you chose a power of the cyclotomic character, and someone else chooses a different power, those are two different integers mod p minus 1. They don't deform into each other. But you can also kind of choose an unramified character. I think, no, Toby called it alpha. And then maybe I can, if I wanted to fix a determinant, maybe I'm going to fix a determinant to be cyclo to the I. Just that's a possible determinant. So then I would put the inverse unramified character here. And now we're already writing something down where, see, what do I mean when I write alpha? This comes back to the question that you can debate as in high school and you can debate as undergraduates. What is x? Is x a specific but unspecified number, whatever that means, or is it a variable, whatever that means? I mean, I think before the 20th century, nobody asked or bothered to think about such things, and maybe in future centuries, they also won't. But for us, it's kind of a thing, like what is this alpha? And so as Toby kind of explained, for a Galois representation, this alpha has to be a specific but unspecified number in FP bar star. But it cannot be a variable over FP bar because you cannot raise a variable to the z hat powers. You can only raise a variable to the z powers. On the other hand, if you forget about z hat and z, and you go back to your kind of common sense intuition about mathematics, if you write a symbol and you're allowed to write it as a symbol, this symbol is a parameter, and something should exist over this parameter space. And so that's the basic picture that makes you think this stack kind of exists. And then you can make these extensions, and as Toby explained, apart from some very degenerate special choices for alpha, so some specific specified choices of alpha and I, apart from some very specific choices of alpha and I, this extension class, if it's non-trivial, is unique. So there's an obvious sense in which, so again, like people here of a certain age will have gone to lots and lots of lectures where somebody wrote down this Galois representation and wrote this, and they didn't specify anything more, and so you know what they're talking about. They're giving you a lecture about this family of Galois representations, which is the unique non-split extension of these things. So again, they're talking about a family of Galois representations that that exists in their mind and on the board and in the audience's mind, so it must exist in mathematics. And so that's the family of phi-gamma modules. Those are the kind of families that we made. So these families obviously existed. The question was just, how do you actually write them down with whatever the current tools of mathematics are? And so that was the point of using phi-gamma modules. And the one thing that was kind of surprising, I think, to us back in 2011, and maybe still is sort of a bit unexpected, is that you can move this thing, so you can vary this alpha, and you can have this, and now I've set the star to be non-zero. I can deform this to become irreducible. And that's a phenomenon that can't happen in representations of groups. So if you have a family of reducible two-dimensional representations of some group and you take a limit, the limiting object will be also reducible. And if you want a formal proof, one way to prove it is to say that if you have a plane, something two-dimensional with a group acting, and you have an invariant line, so that means there's a Grassmannian of lines in this plane, and now the group is fixing this line, so that's a closed condition. Each group element is fixing the line. That's a whole bunch of closed conditions, and that's a closed condition. And the Grassmannian is proper. So when you take a limit, you get a point of the Grassmannian that's invariant in the limit. And so that means the limiting representation will also have an invariant line. And so, but in our stack, that doesn't have to happen. So our stack is not the stack of representations of a group. And so it really is something sort of it behaves somehow differently. But this phenomenon was a kind of a known phenomenon. So it certainly was sort of, you can write, again, it was something that goes back to the work of Fontaine and Lafay. You can just write down a family of Fontaine and Lafay modules depending on a parameter. And for a special value of the parameter, the Fontaine and Lafay module is irreducible. But for generic value of the parameter, the Fontaine and Lafay module is reducible. And that's one way to kind of write down such a family. And so in this picture, this row bar is irreducible. And it has two Serre weights. And you can write this, so this irreducible point, this point here is a point in our stack which corresponds to that irreducible Galois representation over there labeled by irreducible. And that, right, there's a family of reducible Galois representations degenerating to it. There's an I that we chose. But there's actually two such families. So there's another family that has the same limit with a different choice of I. And that's, the fact that there are two families is why this irreducible has sort of two Serre weights. And that's what these two lines are. So these two lines are kind of the two different families of reducible Galois representations that limit to this irreducible Galois representation. And another sort of impetus for thinking about this stack was that when one was making arguments in Galois deformation theory, you would encounter these pairs of lines. You would be writing down Galois deformation rings, and they might have equations like xy equals p. And when you set p equals 0, they become xy equals 0. And so you see these two lines, but you would only see the formal completion of these two lines at this point. So you would see a ring like zp double brackets xy with xy equals p. And then you mod p, you will get fp double brackets xy with xy equals 0. And so that will be not what I've drawn here, but that will be the formal completion of these two lines crossing at this point. And you somehow, in this Galois deformation ring, you could never get to these, you could never somehow get to these two lines. So you would somehow be working at this irreducible point. You would have the feeling that if you could just stretch far enough, there were reducible Galois representations that you could argue with. They would communicate with your irreducible Galois representation and tell you things. And if you wanted to sort of focus on, say, one Serre weight over the other, you had this feeling you could just stretch out and try to reach the reducible Galois representations that had that one Serre weight, but not this Serre weight. But you couldn't do it on this ring. This ring never escapes the origin, really. There's some, like, That's the formal completion. So again, this stack sort of captured was made to capture the idea that you could really move out of your row bar to these other row bars that were we already was sort of seeing them suggestively in traditional Galois deformation theory arguments, but they were not somehow there mathematically. And so this stack puts them there. So that's sort of what this stack is doing, and that's how it, that's sort of where it came from. And when we began, we were really, at least, I can't speak totally for Toby, but at least for me, very much just trying to understand this idea of moving out from a specific row bar that might have a lot of Sayre weights, trying to access a more generic row bar that had only one Sayre weight, because that would be easier to think about. And so definitely didn't expect it would have anything to do with the categorified local Langlands program, which I didn't ever imagine would, I mean, it's not that I didn't imagine it was a thing, it was that was not completely an unknown thing at the time. But one thing is that it seemed kind of important to us at the time that we were really moving in these families of row bars, and that you really had these two lines crossing. And so it seemed that, for example, in the global context, there wouldn't be interesting stacks. Because, see, if you subtract this dimension from this dimension, the number you get, like for example here, 3 minus 1 is 2. 2 is what the dimension of a global Galois deformation ring for Galois representations attached to modular forms will be. So if you take the p torsion in the elliptic curve x011, that's a mod p representation of the Galois group of Q unramified outside P and 11, and that has a Galois deformation ring, which will be two-dimensional. And I guess we don't have colored chalk here, but this? No, now I have to try and use it wisely, so we'll see if I can do that. But okay, so just to choose a point that's not in the intersection, because it's going to make the diagram slightly less messy if I work at this point. If you have global Galois representations, you can restrict them to the Galois group at P to get local ones. And so and see 2 is a complementary dimension to 1 inside 3. And that's actually what happens. So the global thing, when you map it to the local thing, those maps are actually always finite. For GL2, that was a theorem of Vidas Pascunas, and in general, more generally, it's a theorem of Patrick Allen and Frank Caligari. So you can basically imagine the global thing actually is a closed immersion into the local thing. It's not much loss of generality to have that as a picture. And then but then it turns out the global guys intersect our kind of algebraic skeleton of our stack in points. So the global guys are kind of purely formal. And one reason that's true is that, well, if you now, well, in your mind, I don't know if anyone had a base field, but officially my base field up to now had just been FP, because I said I got rid of a +1 by setting P equals 0. But now imagine that we want to have the base field become QP to talk about p-adic representations, and then what these would have become families of crystalline representations. And the other two dimensions would have been like taking something crystalline and deforming it to stop being crystalline. And so, but we know that if you take a global Galois representation unramified outside P and 11, and it's also crystalline at P, by Fontaine-Meza conjecture, it has to come from a modular form, from an eigenform of level like 11, basically. And there's a finite, or P times 11 or whatever, and there's a finite number of such eigenforms, so there could only be a finite number of those yellow points. Because those yellow points will be where the global thing is intersecting the crystalline locus. So that means that the kind of global yellow two-dimensional thing kind of has to be transverse to the white thing. Actually, that was how Maser and Fontaine, or Fontaine and Maser were led. It's one of the ways they were led to make their conjecture. They knew that these dimensions were kind of complementary dimensions, and there was, at the time, very, very strong evidence for the conjecture, given how little evidence there was for the conjecture at the time. And so because of that, you kind of think, okay, well, like the global stacks, even once you've introduced this local stack that has kind of interesting algebraic families of Galois representations, of local Galois representations, you kind of feel that the global stack will be basically purely formal and so not look any different to a deformation ring. But that's not true. So this is something that was understood in a way by Carl Wang Erichsen in his thesis. He actually constructed stacks of both local and global Galois representations, which in the local case were different to Toby and my stacks in that they're smaller because in light of our construction, so reinterpreting what he did in terms of our construction, in the local case, what Carl Wang Erichsen did was find the maximal substacks of our stack where you actually have Galois representations and not just phi gamma modules. And in the global case, he also constructed stacks of Galois representations, and those turn out to be, I think, really interesting. And it's interesting to think about them even when they're not much more than a Galois deformation ring. And so that's where I want to kind of really start my lecture, which is to talk about local-global compatibility for these stacks, the stacks Toby talked about. I'm going to talk about Carl's stacks, and also at least mention some amplification of them that Eugen and I are writing, and then also the stacks that Eugen talked about will be in the picture too. But maybe just to start, I can say that we can define stacks of global Galois representations. So I'm going to label them this way. So the stack is going to be X. This is just a calligraphic X. There's no relation to the various font choices in the previous talk. Because thankfully, I don't need more than one font. Otherwise, I'd be in big trouble. So, and then we're going to label it with a G. So G is going to be a choice of group. And in some sense, just like in Toby's talk, I'd be in a way happy to have G just be GLN. Actually, in my mind, it's basically PGL2 because I was trained in the era when you learned modular curves. In fact, WeTech probably remembers that, like when we were grad students, there were two really active number theorists at Harvard who had, Barry Maser and Dick Gross, and the students had never talked math really because somehow, like one group was doing modular curves and modular forms, the other was doing something strange like the Langlands program and automorphic forms. You could never talk to them, and so I'd be happy in a way for this G to be like GLD, except that actually, as people know, like apart from GL2, that wouldn't give you Chamorro varieties. So in some sense, this G, you want flexibility in this G, even if you're only a GL2 or GLD person, because you want to allow interesting Chamorro varieties. So we'll have a group G. Of course, if you're kind of more mature, then you just want G to be general anyway. And then I'll work over the global field Q just because it's interesting enough. And then S will be a finite set of primes where I'll be allowing ramification. And S will include the Archimedean prime, always. And then I'll be doing p-adic representation. So S will always include P. And then S can include other primes of ramification that you may or may not want to throw in. And so this is just going to take an input A, which will be some ZP algebra, or just like in Toby's talk, it will be finite type over some Z mod P to the A. And it's going to produce Galois representations. So we'll look at Galois representations, the maximal Galois group of Q unramified outside of S, into A points. Well, there are things you could imagine putting here, like you could put the dual group, or you could put the L group. the thing that's maybe the best thing to put, which is why I've put it there, is the C group, which is this nice modification of the L group introduced by Toby and Kevin Buzzard, as far as I know. And then it appears in Jin Wen's notes, and it's also briefly sketched, reminded of in our notes. But if you don't know the C group, I'll do it in a minute. I'll talk about the PGL2 case, but you should best imagine the dual group, essentially, or the L group. And I want to look at homomorphisms into the C group, and I want them to be, as is usual. Well, I don't know if people say C homomorphism, so I'm still going to say L homomorphism. Just meaning that, just like with L groups, this thing has some semi-direct factor, which is the Galois group, and you want the composite of this map and the map to the semi-direct factor to be the identity. So just to say, if G equals PGL2, then this condition is it's asking that you have a two-dimensional representation and you want the determinant to be inverse cyclo. That's the so that's what the C group kind of ends up giving you in the case of PGL2, and so that's very natural because like PGL2 is the most basic kind of classical case of that will be Galois modular forms with trivial Nabin typists, and they give you elliptic curves. Maybe if you weight 2, you get elliptic curves, and elliptic curves. The tape module has cyclotomic determinant, or the dual tape module has inverse cyclotomic determinant, and so that's why this is a very natural condition. So, so we have this thing, and now what I've written there is a groupoid, and what are so Carl and Erickson showed that X is a formal algebraic stack, essentially. I should say for G equals G or D. And what structure comes from G-hat conjugation? Which structure comes from that? Yes. Yeah, the groupoid structure, or the groupoid structures, yeah, exactly. It's G-hat conjugation, yes. I'm not going to try and bring the board down to write that, but yes, the groupoid structure comes from G-hat conjugation. In the D-dimensional case, it's just isomorphism of representations. And then you get a formal algebraic stack, and so Jin Wen and I have thought about / are thinking about these just for general G and thinking about the derived aspects, so defining them as derived stacks, which is actually going to be important. And so there'll be, the upshot is that there'll be derived formal algebraic stacks. And again, in the G or D case, the underlying classical stack will be the thing that Carl constructed. One thing to say is that, so in Toby's lecture, the stacks he wrote down, he didn't talk about them all as derived stacks. But if you were, so I'm not going to claim that it's a trivial thing to then try and redo the theory with derived things. It's probably, at least for me, that will be non-trivial. But what one can say with certainty is that in the end, if you redid all of Toby and my stacks in a derived setting, you end up getting the same stacks, and they actually don't have a derived structure. So you take the same stacks, you just can also evaluate those same stacks on derived rings, and you get whatever you get, but you don't, the stacks don't get any derived enhancement. It's just, and this is, I think Eugen would have explained the same thing in his lecture for the kind of local stacks of local parameters for L not equal to P for a reductive group. The stacks, even though you define them a priori in the derived world, they end up being classical. But in the global case, these stacks will typically be derived, and that's important. They'll have non-trivial derived structure sheaves, and those derived structure sheaves will play a role. So yeah, so again, this X means like X, G, Q, S. And so one thing you can do with a representation is you can take its trace, or its pseudo-representation. So you can map to the space of pseudo-representations, which I guess for general G was worked out carefully, I think, by Versala-Fogg. But for GLD was worked out carefully by Chenevier, and for GL2 goes back to work of Wilde and then Taylor. But so this is, so you have your Galois representation, and you have an associated character or trace. And so this is the moduli space of traces. And that's just a formal scheme. And in fact, the theorem of Chenevier shows that if you work mod P, so if you mod P and you have the trace of a representation, of a Galois representation, it certainly has formal deformations, but it has no algebraic deformations. The deformations are purely formal. If you like, the reason is that, like for example, so for GL1, where the trace and the representation are the same thing, because the trace of a 1-by-1 matrix is just the 1-by-1 matrix. So for GL1, this thing will be entirely just formal, like it'll just be formal completion of points. And so the reason, if you like, is like in the global function field case, the global Weil group has a kind of a Z quotient, and Z emits interesting deformations. But somehow the GQS just has nothing like a Z quotient. And so there's just somehow GQS is so profinite that there's no room for it to have kind of deformations that really depend honestly on an algebraic parameter in the level of traces. And so this guy is purely formal, but it can have connected components, because for a given S, there can be a bunch of different mod P Galois representations for this S, and so you get a bunch of connected components. So this thing is a disjoint union over the various pseudo representations or traces. So I think this, I don't know why I called it theta in my notes, but I did, so I'll call it theta. So that's a pseudo representation. So here we kind of have a representation goes to its trace, theta. And this is a disjoint union, and so when we pull back, this X becomes a disjoint union of connected components. And so this X, and so each component is kind of the family of Galois representations whose mod P trace is this theta bar. So what you could imagine is you could take P to be 5, and S to be infinity, 5 and 11, and this PGO2 case. And you'll be thinking about, and we could take our theta to be like the trivial plus the inverse cyclotomic character. And we'd be looking at like 5-adic deformations, or 2-dimensional 5-adic Galois representations whose trace was like a deformation of the trivial plus cyclotomic. So for example, in characteristic 0, you could take the trivial plus the cyclotomic. Or you could take an extension of the trivial plus the cyclotomic coming from Kummer theory at 11, 5-adic Kummer theory at 11. Or you could take X011, and you could take its 5-adic tape module. So it's a famous computation that the 5-adic tape module of X011 is also a deformation of trivial plus inverse cyclotomic. So you get some, so you kind of, for each of these theta bars, you get some Galois representations, and you get some stack. And that's the kind of thing this is. And there's an easiest case, is when this trace is kind of the trace of an irreducible representation. So if this trace is really the trace of an irreducible representation, then there's not really any difference between Galois representations and traces when you're deforming an irreducible representation. And so then in this case, the X theta bar would be the deformation ring of R rho bar. So the deformation ring, the universal, not the deformation ring, but the spurf. The X theta will be the spurf of the universal deformation ring of this irreducible representation. That's what the trace, that's what the deformations of the trace would be. But the stack will be very slightly different. So let me say two-dimensional, just again to be my special case of PGO2. And so again, take the determinant to be cyclo to the -1. So then the X will be a stack and as I said, when I'm doing two-dimensional reps, but the determinant is fixed, the automorphisms are the center of SL2, and that's mu2. So the stack will be the universal deformation space modulo a trivial action of mu2. So this is acting trivial. And the map where you remember the trace will be for getting the mu2 action. So that's kind of that's maybe the sort of easiest case of this picture. And maybe I can give one other. So that's the actual, although it's kind of pretty trivial, it's the main case I'm going to be using later in the lecture. But let me show you one other example. So if I was to do the example I said where S is infinity, 5, and 11, and theta equals 1 plus inverse cyclotomic, and I look at X theta, and I want to put in one more condition, is I want to put in the condition of being finite flat at 5, which is one more condition on the representations I want to impose. Then this thing here would look like the following picture. So what I've just drawn there is a closed unit disk. And that's the kind of generic fiber of a formal A1 over Z5. So the sort of rigid analytic generic fiber of a formal A1 over Z5 is a closed unit disk. And what I've drawn here is an annulus of outer radius 1 and inner radius 1 over 25. And that's also that's the rigid analytic fiber of Z fiber join XY with the equation X times Y equals 25. And what I'm drawing now is kind of how that generic fiber specializes to its special fiber. And so I've drawn this closed unit disk in characteristic 0 specializing to A1 over F5. And maybe I should draw this disk in yellow, this annulus in yellow. So here's an annulus. And as we know, when you specialize an annulus to characteristic P, you get two lines crossing. So there's two lines crossing, and there's one of them, and there's the other one. And then the only thing I should do is actually tell you that one of those lines coincides with the white line. And so what I've drawn is an annulus specializing to two lines crossing, and a disk specializing to a line. And one of the line of the disk is glued with one of the two lines in the specialization of the annulus. That's what the picture is. And the whole thing has a kind of action of GM by kind of rotation of this disk and rotation of this annulus. So that's what the stack looks like in that case. And this corresponds to the dual to the 5-adic tape module of X011 that I've been mentioning, and this corresponds to the Eisenstein series. If you like, it's the extension of 1 by inverse cyclotomic that comes from where this is a Kummer class coming from 11 over the 5 power roots of 11. So I don't want to really dwell on exactly why that's the picture, but that's to give you a feeling of what the stack could look like if the theta was not irreducible. And no, there's no derived structure, but if we're done 2 primes instead of just 11, if we're done, so in some sense this has to do with weight 2 forms on gamma 0, 11. If we're done weight 2 forms on gamma 0, n, where n is square free, this will be higher dimensional, the Eisenstein part, and then it will carry derived structure. Because it will be larger than expected dimension, and being larger than expected dimension is basically the indicator that you have non-trivial derived structure. So that's so now I have to do this whole thing where I feel like I'm kind of on a ship. Okay. Excellent. And so my title is there, which is good because that's what I want to do. So I can do that. Is it visible? Okay. So good. So now we can do local global compatibility. So this is an assumption. Let's assume that G gives a Shimura variety. I mean, more precisely, let's assume she emits a Shimura datum, and I've chosen the Shimura datum. So like, the PGO2 is fine. Then I'm getting modular curves. And so I'm going to choose a level. So my level, it will be K, but it will be a level at P, and then a product over levels different from P. And I'm going to choose a weight. It's like in the sense of weight of a modular form, but we kind of know by Shimura theory, if you like, or so on, that choosing a weight is exactly choosing a like a highest weight. Like weight K modular forms correspond to cohomology of modular curves with coefficients in sim K minus 2. Sim K minus 2 is a highest weight representation of GO2. So my weight is a highest weight representation. So I think Eugen called it V sub chi, so I'll call it V sub chi. And maybe I'll choose a lattice in that highest weight representation. So a GO2 ZP invariant, or in general, G of ZP invariant lattice. And so that's a lattice in V psi. And it's kind of useful to also have some kind of type, which I mean in a very imprecise sense. So what I mean by a type is just some tau, which is a tensor product, kind of a tensor product over the primes in the finite primes in S of tau V, where this tau V is a smooth rep of KV. And maybe I should choose lattices too. And so basically, the weight lets you choose a kind of a weight, in the sense, I mean, weight. And these types let you choose level structure or let you fine-tune the level structure to get different kind of fine-tuned ramification information at different levels. The key thing is that this has an action of Kp, and these things have actions of all the Kvs. So So using that, we can draw a big diagram with all this data. So first of all, we have our global stack. And then we can restrict our global Galois representations to local ones. So we could restrict them to the Galois group at an unramified prime, but that doesn't really add anything to the picture. So I'm not going to think about those primes. I'm going to restrict to where I have ramification, because that's where it's kind of interesting. So I restrict to these local stacks. So this xv means the stack of Langlands parameters for well, so if v is different from p, I think Eugen explained this in his talk. So it's the Langlands parameters for the local Galois group at the prime v. And when v equals p, it's going to be what Toby explained. And so I should probably assume that g locally at p is isomorphic to sort of GLD, which already basically, or p GLD, or you could do GLD plus GM, sort of various simple modifications of GLD. So probably in practice, my G should be kind of modular curves or unitary Shumor variety. And then now we're going to believe we have all these conjectures. We're going to believe we have all these categorical Langlands conjectures. And so over this guy, I can make sheaves. To make a sheaf, I need to input a representation, but I have the data for that. So, at a place v different from p, I have this tau v circ, and I can compactly induce it from kv, which is a representation of, to g of qv. And I can take the associated sheaf that should conjecturally exist by this fully faithful functor that takes representations into coherent sheaves. And then I can so I can put that coherent sheaf on the factor at v, and then I can kind of tensor them together over the exterior tensor them over these various factors. So this is over the v not equal to p. And then at p, I can do a similar induction where now I have kind of two representations. I have my type and I have my weight. So I have v0 xi tensor tau 0 p. And that whole thing is like has quite a lot of symbols in it, so I can shorten it to A. And so I have this coherent sheaf A on this product. And I could pull it back. I could do a shriek pullback and pull it back to get a global coherent sheaf.
Sorry, but it's a little hard to see what you have written there. What's the difference between v equals p and v?
Sorry, when v equals p, you include the type and the weight.
So you're tensoring?
Yeah, they just tensor together.
They tensor.
Yeah. And so here's a conjecture which is a kind of a local global compatibility conjecture. So what we might be interested in for the Shumor variety is we might be interested in, so I'll write y of k for the Shumor variety at level k. And I use y just because for modular form people, like y is a traditional notion for the open modular curve, which is the actual Shumor variety and not its compactification. So this is the Shumor variety of level k. And I'm going to take coefficients in a local system that comes from these are, I have I can make a local system coming out of the weight and out of all these types. And so that's the kind of thing you might want to compute. It's the cohomology of a Shimon variety, so it also, this C means compactly supported. So you could also think of it as the homology, if you like. It's dual. So like in Eugen's talk, he had kind of a cohomology and homology, so you could think of this as being the homology. And it has for example, a Galois action on it. And of course, number theorists expend quite a bit of effort trying to compute this thing in different contexts and using it to prove other theorems. But so the conjecture is that it's canonically isomorphic to a different cohomology. So this cohomology is cohomology on our global stack. And the thing we're going to take cohomology of is basically this F upper streak. So, but I'm going to modify it slightly. So, but just to say, already you can see that perhaps there's something slightly missing because we didn't include anything to do with the prime at infinity. And also we're supposed to get a Galois action here, and there's no Galois action. But this guy comes with a Galois representation. This is a moduli stack of representations into the C group of G. And and we have a Shimura datum. And one of the jobs of the Shimura datum is a co-weight into the group. So it's a weight of the dual group. So one of the jobs of the Shimura datum is to give you an highest weight representation of the dual group. So that when you have a representation into the dual group and you have the Shimura datum, you can convert it into an actual vector space like you have a Galois representation into the dual group, but now the Shimura datum gives you a vector space representation of the dual group. And so the composition means you get a actual vector space Galois representation over this guy. So we'll just call that the universal Galois representation. And I'm not going to, we could have more decorations to do with the Shimura datum and so on. But again, the case I care about is the PG, in examples, is PGL2. And then this is just the universal two-dimensional representation living over this guy. So that's why I like this notation. And I can tensor them together. So this is a coherent sheaf. This is a rank 2 bundle. This is a rank, sorry, at least in my PGL2 case, it's a rank 2 bundle over here, which has a Galois representation. And I can take the cohomology of this coherent sheaf over this stack, and that's some complex of modules, of ZP modules, with a Galois action coming from the Galois action here. And so the conjecture is that these are canonically isomorphic. So that's a local global compatibility. And it should satisfy many, any kind of, if you have a question in your mind, oh, is it compatible with respect to this thing? Well, it's a conjecture, so it could be compatible with respect to anything, because it's just a conjecture. But if you ask, is it compatible with this thing, ask yourself if that suggestion is at all sensible. And if it's sensible, then surely the answer is yes. So, for example, there are Hecker actions here, and there are, for example, pseudo-deformation rings here. And we should have like R equals T type theorems connecting to Hecker algebras and pseudo-deformation rings, and this should be compatible with those, for example. So in particular, if I kind of put, if I chose a particular component here, I should get the part of cohomology where I localize the corresponding maximal ideal in the Hecker algebra. And so, so I have like 5 more minutes plus epsilon. Yeah, good.
That's clear, that's possible.
Well, I should, yeah. So I should figure out where I am, at least in my notes. Okay. So I want to, again, think about I'd like to think about this special case. So this special case, again, you might think it's a bit kind of stupid in a way because the stack was not a very exciting stack in this case. But even there it is at the top of the board. the case, but I mean on the top board there. So, but even there's kind of something to see. So in that case, what do we have? Well, let me say again, I want to be two-dimensional and determinate the inverse cycler. So in the old days, we called this situation when this theta is an irreducible Gauss representation, we called it non-Eisenstein. And because Eisenstein series have to kind of do with reducible Gauss representations, and so irreducible Gauss representations are the non-Eisenstein case. So in this non-Eisenstein case, well, we know that the Hecker operators act on the H. Yeah, let's see. Sorry, just a step back. Let's even think where the degrees of cohomology live. So this is an open modular curve. So it's an affine curve. And I'm doing compactly supported cohomology. So I have H1 and H2. That's it. And now, the H2, we know that if L is a prime not in S, then we know that the Lth Hecker operator acts on H2 by 1 plus L. And that's the kind of trace of trivial plus inverse cyclo. So the H2 is Eisenstein. It's entirely living above an M theta bar for theta bar being trivial plus inverse cyclo. So when I'm non-Eisenstein, the H2 localized at a non-Eisenstein guy vanishes. And so on the left-hand side, we just have H1. So we get just the H1 of our modular curve localized at M theta bar. And on the other side, we get, well, what do we get? So I have a picture. So let me just see what my picture says. So my picture says the following thing. So I'm going to write something there, but to kind of write it, I think I need this picture. So I have my SPERF of R rho bar, and that maps to, so what I'm doing here is I'm kind of writing the deformation ring version of this. So in the deformation ring world, I have the product over these primes V of my rho bar locally at V. But then to talk about the deformation ring, I should frame it. So I frame it. And then I am also going to just add some formal power series variables. So I'll just indicate them with dots because they're not super important. And then I'll put a SPERF. Then I have a closed embedding. And maybe I'm going to assume P is at least 5. And in that case, this map is an LCI map. In other words, this guy is cut out in this guy by a regular sequence. And that's a computation with Gauss cohomology. It's probably people like Berkler and Kiss. I'm not sure if it's first due to Berkler or maybe Berkler and then Kissen also did such things. But that's a kind of a basic sort of example. And then this guy maps versally to my product of my XVs, because these are versal rings. And this, of course, maps to my X, which is exactly this thing modulo mu2. And so I can kind of compute this f of a Schrick basically going this way. And so I kind of have my coherent sheaves, and I pull them back to this versal ring, kind of at this versal ring computed around the image of my rho bar. So my point rho bar is mapping to its restrictions. And this is a versal ring to this product at these restrictions, at this kind of tuple of restrictions. And I'm just going this way. And well, you could say, well, if you go this way, it looks slightly bad because you've actually not landed where you're supposed to land. You're kind of going this way. It's the same as like going this way, which means you've kind of pulled back, and then you've like pulled back an extra step. But what this means is that when you have a coherent sheaf here and you pull it back here, well, when you get a coherent sheaf here, you just have a module over this ring. But when it's pulled back from here, it's a module over this ring with an action of mu2. So if you kind of go like this, what you're producing is just a module over R rho bar, so some module over the Galois deformation ring, that has an action of mu2. And a basic principle of the situation is going to be that this mu2, which is a center, acts trivially on that module. And so the mu2 doesn't matter. So when you compute this cohomology, when you compute cohomology on an affine scheme or a formal affine scheme, you just get the module. You have a coherent sheaf, which is this kind of localization of a module. You take the cohomology. By Sayre's vanishing theorem, there's no higher cohomology, and the global sections are just the module you built the coherent sheaf out of. And when you're doing it on this stack, you have this mu2 action, so you do everything I just said, but you also take invariance under the mu2 action. But this mu2 is in the center, it's going to act trivially, kind of by general principles, and so you just get this pullback. And so you find that this gadget is just equal to kind of the kind of versal pullback of A, and then if we call this, let me label them by the kind of labels on the diagram. So it's just the A pullback kind of by this versal map, and then pullback by this LCI map. That's what the H1 is, if the conjecture is true. And you sort of see some interesting things. For example, you see that these pullbacks, which could have, sorry, there should be shrieks here. But you see some interesting things, like because these shriek pullbacks can be derived for sure. But for example, we're actually just getting cohomology like in sort of the bottom degree. And so, well, so one thing is that this is a versal map and this is an LCI map. So those are good for doing F upper shriek. So when you have a smooth morphism, or when you have an LCI morphism, the F upper shriek is just going to be the F upper star with a shift. And the shift will be by kind of some codimensions. And so it's okay to have written star, which is sort of what I originally wrote here. You learn something more because you also kind of learned that this A is in some kind of general position with regard to this LCI map. That's related to the picture I was drawing here. Just for example, I gave a kind of counting argument to show that the intersections of the global and local are proper, but we know more. For example, for GL2, we have multiplicity 1. We often have mod P multiplicity 1. We often know these intersections are transverse, not just proper. And so that's kind of what's a bit happening here, that this pullback by this LCI is still not introducing any higher cohomology, is sort of telling you that the kind of global thing is very well positioned with respect to the local thing and with respect to this sheaf on the local thing. Unfortunately, so I'm going to finish up. I know I have to finish, so I'm going to finish up now. But unfortunately, this map is a closed embedding, so it's not super great by itself for kind of investigating the sheaves here, because you pull them back to these versal rings, and that's beautiful. That's basically like, morally, pulling back to a versal ring is just like studying the behavior of this sheaf in a neighborhood of a point. So that's a beautiful way to study at least the local structure of a sheaf, is to pull it back to a versal ring. But then you slice it with some regular sequence, and that's a little bit destructive. But for other reasons, number theorists invented this thing that Eugen already talked about called Taylor-Wiles patching. And Taylor-Wiles patching is just a process where you get to take this guy, which over here will be this yellow guy, inside the white guy, and then you add auxiliary primes to the level, and suddenly the yellow thing has become a bit thicker. And you add more auxiliary primes, and the yellow thing has become a bit thicker. And in some direct limit of schemes or inverse limit of rings, this yellow thing has actually become the entire white box. So that's kind of what Taylor-Wiles patching does. It's a mechanism that does this. And so it means that you get to here put spurf of R infinity, where this map is an isomorphism. And so then these guys pull back to this kind of thickened cohomology. And this is, so I'll finish up by just saying that that's kind of the comparison with patching. So that was the thing that Toby wrote in one of his kind of conditions on the conjectural functor is it should be compatible with patching. And the compatibility with patching is very related, and basically argued as kind of a consequence of this local global compatibility, but it also explains many properties of the sheaves. Like why should some objects, for example, he said L infinity should be abelian, L infinity should be concentrated in degree 0. That's because here we got cohomology just in the bottom degree here and no higher degrees. And compatibility with duality will come from growth and from Poincare duality on this H1. So basically, all the expected properties of the functor come from kind of this isomorphism, patching, and then just thinking about what you know about cohomology of modular curves. So what I want to talk about next time is how you can do things with that to, what some of these things are, how you can do things with patching and with this functor to learn more about, talk more about the stacks again, about the functor, give you some flavor for how things go. And so maybe what I tried to do a bit in this talk and what I want to do in the next talk is just emphasize that for like at least number theorists of my style, I don't want to be as absolutely anti-categorical as Lenstra, who famously said he started doing number theory knowing he didn't want to represent functors, but then ended up representing functors to solve Cypher-Hinn equations. So I'm probably not as anti-functors as that, but nevertheless, like this I'm not naturally a categorical guy, but these things are kind of, although it can look very austere, this categorical Langlands, it's very concrete and it relates to very, very concrete number theory. And that's what I'm trying to show here and what I'll try to kind of keep showing in the next talk. So thank you.